Hi, I'm Yuan He, currently a PhD candidate at the University of Oxford. The work of this paper is associated with my undergraduate honors project, supervised by Dr. Shai Cohen at the University of Edinburgh. It deals with the English to Chinese transliteration task. The first thing is to explain our task in the paper, that is transliteration. The translation of the named entity is mostly based on pronunciations. For example, in the table, we have an English name, Amy, transliterated into Chinese, Aimee, and the corresponding pronunciations in IPA for English and in Pinyin for Chinese are presented in later two columns. Note that the IPA stands for International Phonetic Alphabets, and Pinyin is the phonetic writing system for Mandarin. As you can hear, the pronunciations of the named entity in English and Chinese are quite similar to each other. The general motivations for transliteration are shown below. It plays an important role in tasks such as information retrieval, address verification, and machine translation. So, why study English to Chinese transliteration? The reason is that it is challenging because English is an alphabetical language, whereas Chinese is a logographic language. Each Chinese character is a logogram that represents a whole word or phrase. However, for English, in most scenarios, characters need to form a sequence to really make sense. In the Amy example, we can see that the character A has a pronunciation A, which corresponds to a target logogram I, and the subsequent MY has a pronunciation Me, which corresponds to a target logogram Me. So each target Chinese character has a concrete, independent pronunciation, while this is not the case for English characters. In this slide, we summarize our contributions as follows. First, we found a new English to Chinese dataset which was extracted from a giant dictionary. We name it as DICT dataset. You can find it available at the URL here. Second, we developed a new evaluation metric specific to our task, which gives a better estimation of the system's quality than the traditional one. We'll explain it later. Third, we designed a multitask learning transliteration model, which attains similar performance as the previous state-of-the-art while having a much smaller model size. Before delving into the details of our model, we shall introduce certain related work in this slide. Early in 1997, researchers started to use sound representation as an intermediate before transliterating from source name to target name. Later on, there are instances of using both the graphemes and phonemes in the design of transliteration model. Also, incorporating phonetic features has been proven beneficial by certain research work such as the ones shown here. Finally, we are also motivated by the previous success of multitask learning application on NLP tasks. The core idea of this paper is to incorporate sound information in the model design. Why is sound information important or helpful? There's actually an intuitive understanding that most of the transliterations are based on pronunciation instead of meaning. The Amy example we have shown before is a typical case where the target word pronunciation is very close to the source word pronunciation. So how could we include the sound information in the transliteration model? Our approach in this paper utilizes a theory in multitask learning that training closely related tasks can improve performance on both. To be specific, we define English to Chinese transliteration as a main task, and English to Pinyin as the auxiliary task, and train them together. In the example below, the lowercase tokenized input source word, Howard, is converted to 霍华德 in Chinese and 霍华德 in Pinyin simultaneously. Note that the pinyin we use here is the one without tone mark. We shall use the Howard example to present our model in the slide, where you can see that the source name Howard is fed into the shared encoder, which connects to two different decoders via separate bridge layers. The dual decoders here correspond to the main task and the auxiliary task transliterations, respectively. The output log probes are then fed into the customized loss function, which is a linear combination of the main task loss and the auxiliary task loss. The underlying idea is that by chaining the source to target and source to sound mappings together, the shared encoder is expected to generalize better and pass more refined information to the decoders. Next, we will talk about the evaluation metric we designed for English to Chinese transliteration. The traditional evaluation metric for transliteration is simply counting the portion of exact matches, that is, the word accuracy. The problem is, if the dataset only contains one possible reference for a given input, then the alternative answers are all omitted. So how about including more references? Well, this is also unrealistic because we can't expect our dataset to include all possible transliterations for any given source name. So our metric accuracy was alternating character table, abbreviated as ACC-ACT. It's designed to solve the problem to a considerable extent. The alternating character table, abbreviated as ACT, we mentioned in the previous slide, is a table with each row storing a list of interchangeable characters. This table only makes sense in a logographic system where characters are independent. We created the table based on the DICT dataset, and we think this table can be further improved by linguists. Here is an example of how to apply the ACC-ACT algorithm. The source name Mona has two possible transliterations, Mona and Mona in Chinese, where distinct characters occur in the same position. Suppose the model predicts the second transliteration, while the dataset only includes the first one. The algorithm will be first trying to identify if the prediction and the reference are of the same length. If so, it will check if the distinct characters are in the same position. In our example, the distinct characters occur in the second position. Next, the algorithm will look up to the ACT to see if the distinct characters are an alternative to each other. If so, replace the character and see if it matches the reference. We conduct our experiments on two different datasets. One is the DICT dataset we mentioned previously, and the other is the news dataset originated from the News 2018 shared task. We use a script provided by Grundiget and Heathfield to pre-process the raw data so that we can compare our model's performance with theirs. Their model achieved top performance on several transliteration tasks in the shared task. Note that we have no access to the official news testset, and only when we submit the transliteration result will we see the scores. And we use the official development set as the internal test set for news experiments. To select the best multitask model, we tune the lambda value in the loss function on the development set of DICT and news datasets, respectively. The following plots demonstrate the relationship between the main task and the auxiliary task. The y-axis represents the main task accuracy, and the x-axis represents the auxiliary task accuracy. The data points here were taken from the evaluation steps on the development set, with colors indicating models of different lambda values. It's clear that the main task accuracy is increased with the auxiliary task accuracy for all lambda values, and that is for all our models. This shows that training these two tasks simultaneously does benefit the performance on both. The experiment results on the new official development set is shown here, where you can see there are 3 different scores for main task and only 1 score for auxiliary task. The ACT here stands for the traditional word accuracy. ACC Plus stands for the accuracy that considers multiple references existed in the dataset. And the new dataset does have multiple references for some names. ACC-ACT stands for the adaptive evaluation matrix we mentioned in the previous slide. The reason for having only ACC for the auxiliary task is that the other 2 matrices do not make sense here. From the table, we can see that our multitask model beats our baseline model on all the evaluation metrics. The baseline model here represents the single main task or auxiliary task model. That is simply the case for lambda equal to 1 or 0. Also, the multitask model beats the BiDICT model of the previous work. In the paper of Graduate and Hayfield, they implemented the BiDICT model as their baseline and applied several machine translation techniques to improve it. And that is the BiDICT Plus here. We reproduce their baseline BiDICT and present the scores here. However, the score for BiDICT Plus is reported according to their paper. Our model surpasses their baseline BiDICT, but it does not beat the BiDICT Plus on the official development set. Nevertheless, on the anonymized official test set, our model ranked top in the F score and ranked second in ACC+. While the difference in the scores are not prominent, our model is of 6 times smaller size than theirs. On the DICT dataset, none of the models are indeed outstanding, and we think the reason might be that the DICT dataset only contains names of people, and the noise pattern is not complex enough to reflect the learning ability of different models. To conclude, our work demonstrates that phonetic feature is useful in transliteration. However, the multitask model is not consistently better than the single-task one, especially on the irregular cases where transliterations are based on conventions or historical reasons rather than pronunciations. Also, if you take a closer look at the previous slides, you will observe that ACC-ACT is always larger than ACC Plus and ACC, which means it captures more acceptable transliterations. Finally, our idea can be generalized to other language pairs as well, because every language has a phonetic system such as IPA for English and Lorenzi for Japanese. Many thanks for paying attention to this presentation.